サインでさえ。ちょっと日本語で説明すると、マティアスさんの、コラボレーティブピアツーピア P2P という話を始めようと思います。で、マティアスは、去年、2016年にも来てもらっていて、その時には、Append-Only-Log か何かを使った確かスピークをしていたんですけど、結構ピアツーピアのマドサイエンティストというか、すごいいろんなことをやってるんです。で、実は Node.js のコアコラボレーターでもあって、コアではストリーム周りをやっています。はい、OK。
Hello, does the translation work? Yes. Something is coming out. I don't know if that part translated very well. Yeah, thank you for coming to my talk. I'm going to talk a little bit about collaborative peer-to-peer, what that means and how we can make offline data structures work with multiple people. I'm Mathias. I go by Mathias online. If you want to talk to me, just go to my Twitter or GitHub, send me a link. I'm happy to reply. Also, you can just talk to me at the conference. That's fine also. I work on this project called the DEP project. I'm what people call the protocol lead there, which means that I do a ton of development there and all kinds of other stuff. But this is about P2P. That, if you don't know, it is a peer-to-peer data protocol that you should check out. It's built on all the things I'll show today, so enough about that. I'm from Denmark. I don't know if anybody's ever heard about Denmark, but some fun facts. It's about the size of Taiwan, so very small. It's like 3 hours end to end, but it only has half the population of Tokyo. So this is a good ratio, 1 day to all you Japanese. Very realistic. So collaboration, peer-to-peer, what does that even mean? So, in the way I'm going to talk about it today, collaboration means basically, you connect with friends or coworkers online, and you do some stuff and share data. And but we're all using peer-to-peer technology. What does peer-to-peer mean? Well, peer-to-peer means that the stuff we'll show can run anywhere, not conflicted to running on servers. It can run on your laptop, on all kinds of devices in the browser. P2P also means that you don't have to trust specific servers. You don't have to trust that they're doing the right thing because it's all in the protocols. It also means that all the data you get when you're collaborating can be verified by itself. And built as that as a first-class citizen. And finally, it means that it can run offline in most cases, so that you can keep adding data, working with data, even though you're not online anymore. So very important. I have a lot of content, so hold on to your brain. It's gonna get interesting, hopefully. So we're gonna go through 3 things. If we have time, but the first thing we'll talk about is basically P2P networking and how we can ensure collaboration layer in the networking layer. Then we'll talk a little bit about something that's very close to my heart called Append-Only Logs, which is a really interesting data structure. And then finally, we'll talk about this really cool thing called hash array map tries, which is a powerful collaboration concept as a data structure. So P2P networking. Hope you're ready. So basically, this kind of encapsulates when we're online in a P2P network, how do we connect to people? How do we find people online? How do we connect to them? How do we trust that we're talking to the right people? So if you're using normal TCP or HTTP or something like that, you probably have a system like this where you have a server somewhere, and that server has a host name, and the host name is what you connect to. So maybe if you have your best friend, you'll have the host name bestfriend.com, and you connect to them. That's the way you would normally do it. But this has a bunch of problems. First of all, it's really hard to run because it has to run servers. You have to buy those domain names, you have to map everything. And also, there's no encryption in this. and we want encryption, maybe you have to set up SSL, stuff like that, but it's really, really tricky and hard to scale out. And it doesn't run on laptops, we need to all kinds of infrastructure. It's really annoying. So here's the solution to that problem. Basically, we need to rethink friends a little bit. So what if all our friends had a cryptographic key pair? So if you don't know what a cryptographic key pair is, it's like a secret key and a private key. A secret key and a public key, obviously. And the public key is public, is something you can give out. And the name of our friends we just call a public key because then they can prove that they have a secret key with some magic crypto. It's really smart. Then what they can do is they can take their local IP on their home network or internet and a port and publish that on something called a DHT. If you don't know what a DHT is, it's kind of like a globally distributed database, and I can do a whole talk about that, but let's not worry too much about that. It's just like a very quick way of finding people online on some topic. And then when we want to do encryption, we use something called noise, which is a protocol framework that's very similar to SSL, like HTTPS, but it's much more modular. You can compose it exactly the way you want, and it's not coupled to things. It's really, really nice. A lot of stuff. I made a little module for this. It's called the noise network. And it's really cool because it's a thing where you can do stuff like this. It's really powerful. You can require a module, and then you can generate a key pair. And then you can spin out a server. And then instead of listening on a port, you can just listen on this key pair. And what that does is that it announces you on a DHT, so other people can find you on your public key. And then when they connect to you, it does end-to-end encryption based on this key pair. So you know the people are talking to you. And then you get an encrypted stream you can work with, like in HTTP or other protocols. They're all in a few lines of code. And then you would give out this public key to somebody, and they would find out using this public key in the same way by using a client API, where they would say, hey, cool, just want to connect to some public key. And by connecting to that, the system guarantees that they find only that person with that key pair. And they can be anywhere online or run anywhere. And then anything they would write to the stream would be end-to-end encrypted and totally private. Nobody could listen into what we're talking about. So really powerful. And it does this thing that's probably going to be hard to translate for the machine called P2P hole punching, which basically means it works everywhere. It works even though we have firewalls or nets and all kinds of things. It just works. I have a little demo of that, which hopefully will explain it a little bit better. So here we have the server from the example. It's a little bit differently, but what it does is that it creates a server listening from a key pair, prints out the key of the server, and then when there's a connection, just pipes it out to the terminal, and then it listens for input in the terminal and pipes it back to the stream, creating kind of like a chat, because it takes your input and pipes out your output. Just as an example. So if you run this, let's build up this public key. That's the public key of this server. So now anybody with this public key can connect to the server and they'll do like end-to-end encryption that nobody can get in between. So let's try that. I'm going to copy this public key. Then I'm going to open that client. Just on the example. So this is a client where we can paste in the public key up here, and then it does the same thing as the server. So this will find the server on the DHT, hopefully. Let's try that. I'm just going to paste it in because that's nice and easy. So we're just going to run it. So now they're running. So hopefully if we type something over here, you'll see that it appears both places because they find each other. Christmas. And just to show that this works everywhere, what you can do is you can log into a server or another computer. So I have another computer running in Germany. And I have the same code on here. Same server, but on a different computer, not this computer. And if I run it here also, this server, I'll get a new key pair out. Because we're not storing it, you could store it in a file if you wanted to, or a chain. And then we'll just paste this in here real quick. And even if you run this, hopefully, on 2 different machines, they'll find each other. So you can run this on any kind of machine, or at your home or anywhere, and it's all internally encrypted. So that's basically how we find friends and start collaborating. Awesome. That worked. That was awesome. So let's move on. So we have like a networking layer. You can talk to people. Let's talk a little bit about data structures, because it's, even though we can talk to each other, we probably want to exchange data, and we want to exchange data over time securely. So we need some data structures. And there's this data structure when you do peer-to-peer that's at the center of everything. It's called the Append-Only-Log. It's one of the most important data structures out there because it's really, really simple to understand, and it's super powerful because it allows you to build offline architectures and collaboration architectures really easily once you have this one. So it kind of works like this. Imagine you have a log. I represent a log here by a train. And the only thing you can do to this log is add data. So you can add a piece of data, and the first piece of data is just, it's called 0, but it can contain any kind of data inside. And then it's append only, so the only thing you're allowed to do is add more data, and add more data, and add more data. So it's just like kind of like a tape of data coming out. And then you can read data out of it. So you can say like, oh, what's in 5? And you can open that up and see what's in 5. So it's a really simple data structure. So why is this cool? It's cool because it's really, really easy to share in a P2P network. Because it's very easy to digest what we have. If I talk to somebody else online, I can just be like, I have 1, 2, and 5. And the other person could be like, oh, I have 4. And then we can just exchange what we have. And they're very easy to make secure. And I'll show you a little bit about that. Because basically they're very easy to verify using something called Merkle Trees. So if you've never heard about Merkle Trees, it's this really powerful data structure where what you can do is you can take a series of data and you can build what's, you can hash everyone, you can build what's called a Merkle tree, which is just a tree of hashes. So if you take the first piece of data here, 0, make a hash of that, and a fingerprint. Then you take the next piece of data, you make a hash of that, and then you take these 2 hashes and you hash them together. Can you see? Kind of forms a tree. And you keep doing this, and you keep building a tree. So basically, it takes all the data, it makes fingerprints of all the data, and then it makes fingerprints of the fingerprints until you have one fingerprint at the top that's like a fingerprint of everything. So if you just keep exchanging the top one, you can kind of verify all the data. So assume for a second that we trust that top piece of data, that somebody gave it to us, a link or something, or we got a signed message that says, here's that thing. What if we want to get whatever data is in number 5? It's actually a pretty simple protocol because somebody just needs us to send us the uncles in the tree. I'll show you a little bit what I mean by uncles. So assume we want to get this one. We want to download this one. And we trust the one up in the top, the red one, right? So that one we trust. We want to get this one. Then somebody sends us number 5, sends us data. It's like, oh, cool, data. We don't know if this is good data or bad data. We get this data, and we make a hash of it, a fingerprint. That gives us that one on top, the next one. Then somebody sends us the uncle. If this is the parent, that's the uncle, because they're siblings. Somebody sends us the uncle. Now we have 2 siblings. We make a fingerprint of those 2 and produce the next one. Then somebody sends us the uncle. We make a fingerprint. We get the next one. And somebody sends us that uncle. And we make a fingerprint. And then we combine those 2 together. And if they match up to the red one on top, then we know data hasn't been tampered with. And everything is good. And everything's correct. So like we cannot fake this data. It's completely secure. So basically, you can take a stream of data like this, and you can very easily get it from people you don't trust, because you can verify all of it very easily compared to all kinds of crazy algorithms. And in fact, whatever piece of data you need, you only need a logarithmic amount of uncles to verify anything. So if you have 1 billion pieces of data, you only need 9 uncles. So very, very smart, very efficient. It also means that you can replicate what's called random access, which means you can just get the one you want, not other ones. So like the example before, we just got 5 without having to get any of the other data, which makes it really, really good for building these offline architectures, because we can just do this offline without talking to people. Okay, so why is this important? Because it's just a stream of data. It's kind of hard to understand. Well, it's really important because it's a really powerful abstraction to build things on top of. So once you have a secure layer where you can do these appends, you can build very, very powerful data structures on top of it. I implemented one of these Append-Only-Logs. It's called hypercore. And it kind of works like this, where you call an append method that adds data to that train. And then you can get data out by just putting in the number, and you can open up what's in the box. And the cool thing is they're very easy to share online on P2P network using something like a noise network or streams or anything. You just have to pipe them into the stream with a replicate method. You do this telephone pipe. I have a quick little demo of that. So this is that example from the website. So when we run this, we just get the data out again, because we're putting in data and we're getting it out again. If you run it again, we get the same data out. And if you edit it down here, by number 2 out, for the random 2 source. Show table here instead. No, so it's just an Append-Only-Log. And what you can do is that you can take this data structure, like I said, and you can wrap it in the noise network, so you can share it online. So even though I just ran this some data without being online, just did it without any network, I can share this very easily with friends online. So they can get this data and do something with it by just putting in that pipeline. So when you run this, we'll try to run this and see if this works. We get 2 things out. We get the server's key as before, and then we get a key for the hypercore. We do the verification. So we just go in. To the client. this is a client that does the same thing. It connects to noise server and a hypercore, and then just gets the data out, and then you can start reading the data out locally. If you take this key here, these two keys, and we take this other key. There we go. Paste it in the keys. See if this works. Run this line now. I'll get the data out, and you can kind of see that we can get all the data out because this has a bunch of methods. One of them is called read stream, where you just get all the data out. I can't right now. The cool thing about JavaScript is not that it was. This one just gets all the data out, so we can kind of see that all the data arrives. Oh, offers. And the cool thing is that this works offline, so people can add data to this offline, and you can shut the network down, and you can go on a trip to Taiwan or something where there's bad internet, and you can keep adding data, and then when you get online, they'll just get that little diff, and then you can work with it. Which gets us to the final point of like, what can you build on top of this? You can build a ton of top of these things. But something I really like is something called a hash array net tries, or HAMTs. It's quite a mouthful. It's something called the key value store. If you're not familiar with the key value store, it's basically just a very, very simple database, like simple, but much, much simpler. It's a database that only has this API where you can only insert a value on a key, and you can only get a value out of a key, and then iterate and stuff like that. But very, very basic. And the really, really cool thing about hash array net tries, which is just an implementation of this, is that they can be adapted to run on top of an Append-Only-Log really easily. They run on top of this data structure. And they basically work by taking a fingerprint of a key you're putting in, and then building something called a prefix trie, and inserting a prefix trie based on that. If you want to talk about this, find me in the hallway. I can talk about this for hours. But a prefix trie, if you've never seen it, is something like this, where you insert two values, and then you make this structure where you just kind of show what they share. That's how you can build that key value store. And the cool thing about a hash array net trie is that every time you just insert one value, it only needs to do add one string card to the log. So it's very, very efficient, very, very fast. I think that's my next slide. And to get data out of it, you only need to look again at log entries. So very, very fast to find any kind of data in there. It scales really well. And I made an implementation of this called hypertries that runs on top of an Append-Only-Log. So that way you can kind of build data structures offline. They can do a little bit more than just those Append-Only things. So this is an example where it works kind of like the hypercore. It's built on top of hypercores. You can insert data and you can get data out. And you can insert like billions, trillions of data, and it'll still work really fast because of using that trie. So yeah, they're really fast and they scale really well. And so to kind of see how well this works, I spent some time making a P2P node that takes all of NPM and live indexing all of NPM and putting it into a trie to kind of see if we can make make a P2P clone of everything. And it's called IMS, install my stuff. Yeah, like I said, it's P2P clone. So that uses a bunch of tries to kind of, find, here's, if you want to find a module, you just, look at the key value store, it's that module there, and then you just look for the latest version, or the version based on the package JSON. I had a little demo of that. I think I had just enough time to do it. That's perfect. 5 minutes. I just need 4. So, make a folder here. So you can install, if you install that IMS tool, you get a CLI, so you can do IMS help, and the way it works is that you can just do IMS and then some module name. So here I can do IMS hypercore. I haven't tested it on this network, so this sounds interesting. So the way that works is that this runs a P2P network. You work online on the DHT, find somebody who's sharing the NPM. Make sure it's on the latest version, so we want to get the latest module. Then it connects to that trie thing I talked about, and starts the pre-lookups. And even though this is all running on a P2P network, it's all secure and using all those checks to make sure we're getting exactly the right things. It only takes about 3 seconds to run to install the module from scratch. Okay, but the cool thing is, when you run it again, it's usually really fast to figure out whether it has the latest one. I'll put up this one. So, install something like So basically, this connects to a network, and NPM has 7 million versions of packages in NPM. And even though this is using Append-Only-Log, it only gets exactly the data it needs to find the modules and download them. And the really cool thing about this is that it still works offline, so even when you go offline, you can still install modules. When you're online, you'll just get the latest ones, but it's all seamless because it's P2P. So tries are cool, you should try them out. Might be my best. Yeah, so just a summation. This is like things we talked about. All the modules. I have hundreds more. If you want to talk about modules. Anything with hyper on my GitHub is usually P2P related or collaboration related. So that's my presentation. Thank you so much.
Yeah, it's okay. 結構走りがいますね。前の方まだあるんで座ってください。次の発表に行こうかなと思います。So next time.